Okay, thanks. Hi everyone. Good morning, afternoon, good afternoon, and good evening. I am An-hyuk Jang from Yonsei University, and I'll be moderating today's sessions. Today's session is being recorded. Please keep your microphone muted while the speaker is presenting, and hold all questions until the Q&A at the end. But feel free to type in the chat. I read those questions aloud. And today it is my big pleasure to introduce the speaker today. Professor Soohyun Park is an assistant professor at Sookmyung Women's University. She was a postdoctoral scholar at and received her PhD degree at Korea University. And her research interests are in quantum neural network theory and its applications, software engineering, and programming languages. And wow, there are so many awards I have to read. She serves as an editor for IEEE Communications Surveys and Tutorials, and she was a recipient of ICT Express Best Reviewer Award and KICS HFR Research Paper Award, and IEEE ICTC Best Paper and Best TPC Award, and IEEE Seoul Section Student Paper Contest Awards, IEEE VTS Seoul Chapter Awards, IEEE ICDCS Best Paper, Best Runner-Up Post Paper, and finally IEEE TCSC Award for Excellence in Early Career Researchers. Please join me in welcoming Professor Soohyun Park.
Hello everyone and welcome. My name is Yuan Park from Sookmyung Women's University. Thank you for being here for Quantum Computer System Lecture Series, and thanks to researcher Eun-hyuk Chang for inviting me to speak today. My representation keyword is quantum AI theory and application. I will introduce the basic theory of quantum neural networks and several quantum AI algorithms that my research group has developed. Before starting the technical discussion, let me briefly introduce my research background. I have been actively participating in various academic activities focusing on quantum AI. And my research group, the DPS Lab, focuses on solving various challenges in distributed mobile platforms through AI-driven optimization. We are particularly interested in reinforcement learning, quantum machine learning, and intelligent distributed system design. Within this framework, we actively pursue quantum AI. Also, we actively collaborate with several international research groups. These collaborations cover quantum federated learning, quantum reinforcement learning, quantum security, and distributed quantum AI systems. Specifically, we have a close research partnership with Professor Jung-Won Kim's team at Korea University, as they are one of the leading institutions focusing on quantum AI in Korea. So I highly recommend checking out their work if you are interested in other notable research beyond today's topic. Now, let's dive into the main topic of today's presentation, quantum AI. The talk consists of three parts. First, I will introduce quantum neural network basic concept. Second, I will present several representative quantum AI algorithms with application research. Finally, I will discuss conclusions and future research directions. Before we discuss quantum neural networks in detail, it is helpful to first understand where they belong within the broader quantum algorithm landscape. As you can see on this slide, quantum algorithms can be categorized according to their computational principles rather than their application domains. Among these categories, variation of quantum algorithms, VQA, A hybrid quantum classical optimization framework uses parameterized quantum circuit to solve optimization problems. And PQC-based quantum neural network is one representative example of a variation of quantum algorithm. So we first need to understand how the parameterized quantum circuit operates and how it can be trained. And it is important to note that the term quantum neural network does not refer to a single architecture. QNNs include several architectures such as PQC-based, quantum Boltzmann machine, quantum annealing neural networks, and photonic QNN. While they all aim to perform learning using quantum systems, and these architectures share a common objective, they differ significantly in their computational principle and implementation. Around these architectures, parameterized quantum circuit-based QNNs are currently the most widely studied and actively developed approach. Therefore, in this talk, I will focus on PQC-based quantum neural networks, and I will use the term QNN to refer specifically to PQC-based quantum neural networks. Let's first compare a classical bit and a qubit. A classical bit can only take one of two values, either 0 or 1. In contrast, a qubit can exist in a superposition of both states. We often visualize this quantum state using the blue sphere. In other words, the blue sphere is the geometric representation of a single qubit state. Any points of the surface represents a valid quantum state. Therefore, unlike a classical bit, a qubit can represent infinitely many states. This richer representation space is one reason why quantum machine learning is attractive. Once the qubit is represented on the blue sphere, we can manipulate its state using quantum gates. The rotation gates rotate the quantum state around the x, y, or z axis. In QNNs, these rotation angles are often trainable parameters. And learning useful patterns often requires interactions between multiple qubits. This is achieved through entanglement gate. Entanglement creates correlation between qubits that cannot be represented by independent qubits alone. In most PQC-based QNN, CNAP gates are commonly used to generate entanglement. Now we have discussed qubit, rotation gate, and entanglement gate. Next, we will see how these components are combined to build a PQC-based quantum neural network. Quantum neural network generally has three parts, such as state encoder, parameterized quantum circuit, and measurement part. The first step is encoding. Since quantum circuits cannot directly process classical data, the input must be transformed into quantum state. This process is called quantum state encoding. There are several encoding methods such as basis encoding, amplitude encoding, angle encoding, and data re-enveloping. And then the PQC contains two major types of operations. The first one is rotation gates, and the second one is entanglement gates. And each gate is related to linear or nonlinear transformation rule. After the PQC processing is completed, in measurement parts, we need to convert quantum states into classical outputs to extract information from the quantum state. With this workflow in mind, we can compare a classical neural network and the PQC-based quantum neural network. we can see some functional similarities between their architectures. In a classical neural network, the information, that means data, flows through the input layer, hidden layers, and output layer. Similarly, a quantum neural network consists of a state encoder, parameter-like quantum circuit, and a measurement part. Of course, they are not exact equivalents. Rather, it is more appropriate to think of them as functionally similar components. From an inference perspective, we assume that the model has already been trained. In a classical neural network, the learned parameters are the weight and biases. During inference, the input is transformed through matrix multiplication and activation functions using these fixed parameters. In QNN, the learned parameters are typically the rotation angles of trainable quantum gates inside the PQC. During inference, the encoded quantum state is transformed by these fixed quantum gate parameters and entanglement operation. After this quantum processing, we cannot directly access the quantum state. Therefore, measurement is required to convert the quantum state into classical information. The measurement outcomes are used to estimate probabilities or expectation values, which are then converted into prediction, class scores, or other task-specific inputs. Depending on the application, these outputs may serve as the final prediction or be passed to additional classical processing layers. This naturally raises an important question. How can the QNN be trained? In classical neural network, the model learns by computing gradients through backpropagation and updating its weights and biases to minimize a loss function. This process is possible because hidden vectors can be directly accessed and passed to the next layer. However, as mentioned before, quantum states cannot be directly observed. Before measurement, a qubit exists in a superposition state, and once the measurement is performed, the state collapses into classical information. This makes gradient computation fundamentally different from that of classical neural networks. Another important difference is that quantum measurement is inherently probabilistic. Even if we execute the same quantum circuit multiple times, the measurement outcomes may be different. For example, if we do measurement several times, the repeated measurement of the first qubit may produce outcomes such as +1, +1, -1, +1, +1, and so on. That means a single measurement is probabilistic, and one execution is usually not sufficient. Therefore, the same circuit is executed repeatedly. The number of repeated measurements is referred to as the number of shots. The measurement outcomes obtained from these shots are averaged to estimate an expectation value. This expectation value plays a role similar to an activation output in a classical neural network. It is the quantity that is ultimately used for prediction and loss computation. Once the expectation value is obtained, the loss can be evaluated in the same way as in classical machine learning. The next question is how to compute gradients. Since we cannot directly differentiate through the quantum state, specialized techniques are required. One of the most widely used methods is the parameter shift rule. For each trainable parameter, the quantum circuit is evaluated using slightly shifted parameter values. Since each circuit evaluation still relies on quantum measurements, multiple shots are required to estimate the corresponding expectation values. These expectation values are then used to estimate the gradients of the loss function with respect to each circuit parameter. Once the gradients have been estimated, a classical optimizer such as SGD or ADAM updates the circuit parameters in the same way in classical machine learning. In summary, shots are used to estimate expectation values, and parameter shift rule is used to estimate gradients. And a classical optimizer uses those gradients to update the trainable parameters of the quantum circuit. So far, we have discussed how the QNN operates and how it is trained. However, designing a QNN is not as simple as stacking several quantum gates together. The training stability, convergence behavior, and final performance of a QNN can be significantly affected by several designing choices, including the encoding strategy, the number of qubits, the number of circuit depth, number of entanglements, or the measure variance, and the number of shards. Because these vectors interact with each other in a highly non-trivial manner, manually designing an effective QNN is often challenging. As a result, different application domains may require different QNN architecture and design choices. And we can also think about quantum neural network implementation. Current QNN input experiments are commonly implemented in Python and executed on classical computers, where quantum circuits are often simulated by software libraries such as PennyLane, QuickSkit, Touch Quantum, or TensorFlow Quantum, rather than executed on real quantum hardware. That means in most current QNN experiments, the quantum part is represented as a simulated pixel layer, while training, loss computation, gradient estimation, and optimizations are still performed by classical computing concepts. So, the primary advantage of current pixel-based QNN is not computational speedup, but the potential for expressive quantum feature representation and parameter-efficient learning is enabled by quantum state space and quantum gate operations. In the following sections, I will introduce 4 representative quantum AI research directions: quantum reinforcement learning, quantum convolutional neural networks, quantum federated learning, and quantum neural architecture search. Rather than focusing on mathematical details, I will emphasize the key ideas, motivations, and application results of each approach. Through these case studies, we can better understand both the motivation for quantum AI and the practical impact that QNN-based approaches can provide. The first one is quantum reinforcement learning for network scheduling. Before introducing quantum reinforcement learning, Let me briefly review the basic concept of reinforcement learning. In reinforcement learning, an agent interacts with an environment by repeatedly observing the current state, selecting an action, and receiving a reward. Through this trial and error process, the agent gradually learns a policy that maximizes the long-term cumulative reward. In modern deep reinforcement learning, neural networks are often used as function approximator. In this case, the current state is provided as the input to the neural network, and the network learns the relationship between states and action. Depending on the algorithm, the output may represent action values, action probabilities, or policy decisions. Quantum reinforcement learning follows the same overall framework. The key difference is that the neural network is replaced by a quantum neural network. In quantum reinforcement learning, there are several ways to interpret the measurement outputs of a QNN. Among them, two of the most commonly used approaches are policy measurement and basis measurement. In policy measurement, each qubit is measured individually and produces an expectation value. These values are then used to generate the final action decision. This approach is particularly suitable for binary decision-making problems. In fact, many network scheduling and resource allocation problems can be formulated as a collection of binary decisions, such as whether to allocate a resource, activate a link, or schedule a user. In such case, the measurement outcome of each qubit can be naturally associated with a binary decision variable. However, some reinforcement learning problems require a much larger action space and need more qubits. In these situations, basis measurement provides an alternative representation. Rather than measuring each qubit independently, basis measurement projects the entire quantum state onto one of the computational basis states. For example, an action space containing 8 possible actions can be represented using only 3 qubits because 2 plus 3 equals 8. As a result, basis measurement enables a compact representation of high-dimensional action space while requiring significantly fewer qubits. This property is particularly attractive for quantum reinforcement learning in large-scale network scheduling problems where the number of possible scheduling decisions can grow rapidly. In the previous slide, I introduced basis measurement as a compact way to represent large action space. This work applies that idea to large-scale network scheduling problems involving UAVs, vehicles, and other distributed sensing systems. In such environments, the action space grows exponentially and can easily reach a size 2 for 16 possible actions. If each action is represented individually, the required quantum resource, qubits, becomes prohibitively large. So, by using basis measurement in quantum reinforcement learning, we can reduce the action space of a scheduling problem from 2 for 16 to 16. This makes reinforcement learning much more scalable. As shown by the convergence of the normalized reward, When the action domain is very large, such as 2 to the power 16, and with massive agents, only the quantum-based multi-agent reinforcement learning algorithm is doable. The key idea is simple. Instead of increasing the number of qubits with the number of actions, we use basis measurement to represent exponentially many actions with only a logarithmic number of qubits. Therefore, the proposed quantum reinforcement learning framework becomes much more scalable for large-scale network scheduling problems. The previous example focuses on compressing large action spaces using basis measurement. But this work applies a similar quantum reinforcement learning framework to lightweight satellite networks where computational resources are highly constrained. In this scenario, each satellite must decide which neighboring direction should be selected for data forwarding and routing. To solve this problem, we design a quantum reinforcement learning model using only 4 qubits to represent the available routing action. Unlike the previous study, the primary objective of using quantum reinforcement learning here is not action-based compression. Instead, reducing the number of trainable parameters while maintaining comparative decision-making performance. To evaluate the proposed approach, we compare it with several well-established reinforcement learning algorithms. As shown in the performance curves, the proposed quantum reinforcement learning algorithm achieves performance that is generally comparable to benchmark methods. However, in some scenarios, the proposed method may exhibit slightly lower performance than the best performing classical algorithm. However, the most important observation comes from the total number of trainable parameters. Despite this dramatic reduction in model size, the proposed method still maintains stable learning behavior and comparative performance. This result suggests that quantum neural network-based reinforcement learning can provide a highly parameter-efficient alternative for resource-constrained systems such as satellites. The second one is quantum CNN algorithms for object detection. In this approach, the parameterized quantum circuit in the QNN plays a role similar to the convolutional layers in classical CNN. As the name suggests, quantum CNN is a quantum machine learning model inspired by the convolutional and pooling operations of classical convolutional neural networks. In classical CNN, an input image is processed through convolutional layers, activation functions, pooling layers, and fully connected layers to generate the final prediction. The convolution layers extract local features, while the pooling layers gradually reduce the feature dimension. The quantum CNN follows the similar idea. However, instead of using classical convolutional filters, the feature transformation is performed by a parameterized quantum circuit. Despite their potential, existing quantum CNNs face several practical challenges. For example, when multi-channel data such as RGB images are directly encoded into quantum states, the required number of qubits can increase rapidly. This becomes a significant limitation in current NISQ environments. To address these limitations, we developed a computationally efficient quantum CNN architecture. The proposed model compactly encodes multi-channel algebraic pitches and performs quantum-based feature extraction. In this work, instead of replacing the entire faster RCNN architecture, we only replace the reason proposal network as quantum concept. The VGD16 backbone first extracts feature maps. Since low image cannot be directly processed by quantum circuits, the backbone first generates intermediate convolutional feature maps. These feature maps are processed by the quantum RPN. The quantum RPN generates object proposals with the bounding box like to contain foreground object from the backbone feature maps. After that, each proposed reason is aligned and pulled into a fixed spatial size through RY pooling. The final classification and bounding box regression are still performed by classical fully connected layers. The key idea of this work is the proposed tri-value qubit encoding in quantum RPN. Instead of assigning separate qubits to the RGB channels, tri-value qubit encoding encodes the three channel values into a single qubit using a sequence of rotation gates. As a result, the number of required qubits can be reduced by approximately a factor of 3 compared with conventional encoding approaches. The encoded quantum states are then processed by a parameterized quantum circuit, which performs feature extraction in a manner similar to a convolutional layer in classical CNN. Finally, the measurement results are reconstructed into channel-aligned feature map. This design improves qubit efficiency while maintaining comparability with high-resolution feature extraction under this constraint. And in simulation, we further improve training stability. We additionally employed knowledge distillation. A predefined classical CNN was used as a teacher model, and the quantum CNN was trained to partially mimic the teacher's representation. Here, the parameter gamma controls the relative importance of distillation loss. In summary, the proposed computationally efficient quantum CNN demonstrates that quantum convolution can be integrated into classical object detection pipelines by reducing qubit requirement through tri-value qubit encoding and improving learning stability through heterogeneous knowledge distillation. Now let's move to quantum federated learning. In classical federated learning, multiple devices collaboratively train a machine learning model without sharing their raw data. Each device performs a local training using its own dataset and periodically sends the updated model parameters to the central server. And then the server aggregates these parameters and then distributed the updated global model parameters back to all devices. They share model parameters, not the raw data. Quantum-federated learning follows the same overall framework. The parameters being exchanged correspond to the trainable parameters of the quantum circuit. When we adapt a federated learning framework for mobile systems such as neural networks, wireless channels are often unstable, which can significantly degrade the reliability of parameter transmission. To address this challenge, we replace classical neural network with quantum neural networks, which require fewer trainable parameters while maintaining comparative learning performance. In addition, for adaptive federated learning under unreliable wireless channel, we extended quantum neural network into adaptive quantum neural network that dynamically controls circuit depth by inserting measurements operations within the circuit. Adaptive quantum neural network means that each local model does not necessarily use the full QNN depth. Instead, the effective depth of the QNN is adaptively selected according to the channel condition, and only the parameters of the activated layers participate in federated aggregation. This significantly reduces the communication overhead and improves robustness against transmission errors. As a result, even local models operating on the poor channel show performance improvements over time through the federated learning process. And the parameter alpha means the data non-IID needs. As the value of alpha increases, the local data set becomes more similar, making federated learning easier and improving the performance of all methods. The bottom row evaluates different wireless channel conditions. Although poor channels reduce the transmission reliability of the model parameters, the proposed adaptive quantum federated learning maintains stable performance, demonstrating its robustness to communication impairments. And another perspective in quantum federated learning is to improve performance by selectively choosing the client that participate in aggregation. Aggregation with heterogeneous local model, especially those containing outliers, can significantly degrade overall performance. To address this, we propose a selection strategy that jointly considers data entropy and quantum state fidelity. Here, the entropy captures data imbalance among local models, and the fidelity captures quantum state dissimilarity between the local models and global model. With several performance evaluation, we can check that the proposed method improves both learning stability and overall performance. The last topic is quantum neural network architecture optimization. In classical deep learning, neural architecture search, NAT, was introduced to automatically discover high-performing neural network structure. The same idea can be extended to quantum machine learning, leading to quantum neural architecture such. The goal of quantum knots is to automatically search for effective PQC architecture, including the arrangement of quantum gates, entanglement patterns, and circuit depth. Before discussing quantum neural architecture such, it is important to understand why designing a PQC is challenging. In general, adding more quantum gates increases the expressive capacity of the QNN and enables more complex feature transformation. However, simply increasing the number of gates is not always beneficial. Deeper quantum circuits accumulate more noise, require higher computational costs, and often suffer from the barren-plateau problem, where gradients extremely small and training becomes difficult. In addition, 2-qubit gates play a critical role because they create entanglement and enable interact between qubits. However, effective use of 2-qubit gates can increase circuit complexity. At the same time, the circuit structure must satisfy several architectural constraints. Therefore, parameterized quantum circuit design is a highly complex optimization problem. To find the most effective quantum circuit under limited quantum resource, we propose a two-stage quantum neural architecture such framework. The first stage is a reinforcement learning agent automatically determines the gate placement within a 4-qubit, 4-layer PQC architecture. For its position in the circuit, the agent decides whether to place a single qubit gate, a 2-qubit gate, or no gate at all. These decisions are guided not only by prediction performance, but also the several practical considerations. After determining the gate placement, the second stage focuses on selecting the most effective gate types and circuit configuration. A major challenge is that the parameterized quantum circuit such space grows exponentially with the number of qubits and layers. For 4-qubit and 4-layer circuit, the number of possible architectures become extremely large, making it impractical to train every candidate independently. To address this issue, we adopt the one-shot last principle. Instead of training each candidate architecture separately, we construct a SPARnet that contains all candidate gate operations and allows different architectures to share the same weights. As a result, the SPARnet is trained only once, while many candidates PQCs can be evaluated simultaneously. This significantly reduces the search cost while still enabling efficient exploration of diverse quantum circuit architectures. These results indicate that combining reinforcement learning-based gate placement with one-shot quantum architecture search can effectively identify high-performing PQC structures without executive search by considering the computation resource limit. So far, we've explored how the same quantum neural network framework can be adapted to reinforcement learning, convolution neural network, and federated learning, and other method quantum NAS. Each application addresses a different problem, but all of them aim to exploit the unique properties of quantum representation and parallelized quantum circuit. Finally, I would like to summarize the key lessons learned from these studies and discuss several open challenges that remain for future quantum AI research. To summarize the main message of today's talk, one of the main motivations behind the quantum AI is the potential to exploit richer representation provided by quantum state space. In addition, quantum circuits may offer scalable representation through a probabilistic quantum state and parameter-efficient learning through angle-based optimization. As we have seen in several examples, comparative performance can sometimes be achieved with significantly fewer trainable parameters than classical neural networks. And furthermore, current quantum AI algorithms are still largely performed using classical computation. That is based on hybrid quantum classical framework rather than a fully quantum learning system. In the NIF area, the key challenge is not determining whether quantum AI can fully replace classical AI, but identifying the scenarios in which quantum representations offer meaningful benefit beyond classical approaches. For this reason, hybrid quantum classical AI is expected to play a central role, allowing quantum and classical models to operate in a complementary manner rather than as competing alternatives. From this perspective, several important research challenges still remain open and deserve further investigation. As I just mentioned, we still need to determine which tasks should be assigned to quantum models and which should remain classical. And we also need more resource-efficient quantum neural networks. And another promising direction is the integration of quantum communication into distributed quantum AI systems, enabling quantum-aware collaboration among multiple agents and devices. Furthermore, improving the interpretability and reliability of quantum neural networks remain important challenge before these quantum AI models can be widely deployed in real-world applications. Lastly, looking forward ahead, these advances may enable a new generation of quantum AI applications, including quantum large language models, quantum generative AI, and many other emerging intelligence systems. Yes. Thank you for listening to me for a long time. If you have any questions, please feel free to ask me. me or contact me by email. Thank you.